You know, in C++, just one little line of code can kick off a whole chain of events. Today, we're going to follow the entire life of a C++ object, from the moment it's created all the way to its final goodbye. Let's dive in.
So you've probably typed a line like complex C1 a million times, right? But have you ever really stopped and thought about what the compiler's doing for you? That simple little declaration starts a precise, hidden process, a whole life cycle really, to make sure your object is born, lives, and gets cleaned up perfectly. So what is going on under the hood?
Okay, so every object needs a solid start. It's like building a house. You have to lay the foundation first. If you create an object, but forget to give its data members some sensible starting values, they're just filled with, well, garbage. And that leads to completely unpredictable behavior, random results, and bugs that are an absolute nightmare to track down.
All right, so on this slide, you're looking at two different worlds. On the left, we've got the risky way. You create a special init function, but the huge problem is you, the programmer, have to remember to call it. And let's be honest, we forget things. If you do, that object is just floating around in an invalid state. But on the right, you see the C++ way. Initialization is automatic. It's guaranteed, it's built right in. How?
Well, the hero of this story is the constructor. It's a special kind of function with one and only one mission: to initialize an object the very instant it's created. This guarantees that it starts its life in a valid, predictable state. You never have to worry about calling an init function again because the constructor just runs automatically, every single time.
So let's really nail this down. A constructor's job is initialization. That's it. It's not for doing general calculations or printing things to the screen. It's the gatekeeper that gets the object ready for its life's work. It lays that solid foundation we were talking about, and without it, everything else is built on shaky ground. And here's what makes a constructor so, well, special. There are a few rules. First, its name has to be the exact same as the class name. That's the signal to the compiler. Second, it doesn't have a return type, not even void. Third, you don't call it directly, it's called implicitly, behind the scenes. And finally, and this is super important, it runs only once, right at the very beginning of an object's life. So, what happens if you want to create an object in a few different ways? No problem. C++ has this awesome feature called constructor overloading. For instance, if you declare an object with no arguments, like complex C1, the compiler's smart. It just looks for a constructor that takes 0 parameters and calls that one. Simple. Now, let's build on that. What if you provide a single integer, like complex C2, 10? Well, you guessed it. The compiler scans the options and finds the constructor that's designed to take a single integer argument. It's like having a custom-made entry point for every possible starting scenario. And to complete the picture, if you give it 2 arguments, the compiler picks the constructor that takes 2 parameters. This is a really powerful feature, sometimes called compile-time polymorphism. But really, all that means is the compiler is smart enough to figure out the perfect function to call before your code even runs. It's flexible, and it's incredibly safe. Okay, listen up, because this is a subtle but super critical point. You can set values inside the constructor's curly braces, like you see on the left. But that's assignment. The true C++ way, the more efficient way, is using a member initializer list, like you see on the right. This is true initialization. It builds the member with the correct value from the get-go. And for things like const data members, it's not just better, it's the only way that works. So, object is born, it's been probably initialized, now it's out in the world doing its thing, calling its member functions. But when a function is running, how does it know which object it's working on? Especially if you have a bunch of them. How does an object talk about itself?
The answer is this magic little thing called the this pointer. Think of it as the object's sense of self-awareness. It's a hidden pointer that's automatically available inside every member function, and it always holds the memory address of the object that made the call. It's literally how the object says, me. Let's make this real. Look at this line, c1.sum c2. The function sum is being called by the c1 object. So inside that sum function, the this pointer is pointing directly at c1. When the code says this.real, it's actually saying get the real data member from the c1 object. That's the crucial link between an object's data and its actions. Now, a good object doesn't just run wild. It has to live by a set of rules. And in C++, one of the biggest rules is all about immutability, which is a fancy way of saying unchangeable. We enforce this with the const keyword, making promises that certain things won't be modified. And you've got 3 main ways to use it. First, you can slop it on a data member, which basically makes it read-only after it's been initialized. Second, you can make a whole member function const, which is a promise that calling this function won't change the object's state one bit. And third, you can go all out and make the entire object itself const, locking it down completely. And this isn't just a friendly guideline. The compiler acts like a super strict referee. Check this out. We've got a const object, t1. We're totally allowed to call showRecord on it because that function also has the const promise. But the second we try to call printRecord, which isn't const, the compiler blows the whistle. It throws an error protecting us from accidentally breaking our own rules.
All right, so we're getting to the end of our object's journey. Its final chapter, if you will. There are just a couple more things we need to touch on. First is the idea of an alias, or a nickname. And then, of course, every life has to end, which means every object needs a proper cleanup.
A reference, you'll see it with the ampersand symbol, is basically just a nickname for an object that already exists. It's not a copy, which is awesome for performance, and it's not a pointer, so it's a bit safer and easier to work with. Once you create a reference and attach it to an object, it's locked in for life. They're super useful for passing objects into functions without having to make expensive copies. And that brings us to the final act, the destructor. It's the perfect bookend to the constructor. If the constructor's job is to build everything up, grab memory, open files, the destructor's job is to tear it all down and clean up the mess. Its name is always a tilde followed by the class name, and just like its counterpart, it gets called automatically when the object's life is over. So, we've seen the whole story, right? A safe birth with a constructor, a well-behaved life with this and const, and a clean exit with a destructor. The object's life cycle is totally managed, but that leaves one huge question hanging in the air. What about the actual block of memory where the object was living? Who manages that? Well, that sounds like a story for another time.